Hi, and welcome to Mr. Garofalo's podcast. In this edition, we are picking up with our lesson on modeling relationships with a line, in particular, the section about residuals. So, for most of the classes today, we had gotten somewhere between exercise 8 and 10, so I'm going to pick up there. We'd begun to fill in this table here, and this table was all about learning about something called a residual. Remember from class, a residual is the difference between the actual value minus the predicted value. So we had started by doing 11.8 shoe length, which had an actual height of 65 inches. When we predicted that using the equation, we got 68.49. Now, since that prediction is greater than the actual, we got a negative residual. Now, by comparison, when we predicted 12.2-inch shoe length, we got 69.95. Well, the actual shoe length, the height of that person was 71. So notice in this case, when the prediction is lower than the actual, our residual becomes positive. Okay, so we continue to do this throughout our table, filling in the missing values. We find that we have a mix of positive and negative residuals. And that makes sense because this would tell us that the points are balanced out with some points being above the line and some points being below the line. So we have some over predictions and we have some under predictions. And we don't have any perfect predictions because none of the residuals are zero. Okay. So for question 9, why is the residual in the table's first row positive and in the second row negative? Well, I just briefly discussed this, but in the first row, and the predicted value is lower than the actual, so we get a positive residual. And in the second row, the predicted value is more than the actual, so we get a negative residual. So if you think about how this would appear on our graph, in the first row, the predicted value being lower than the actual, this would mean that the plot is above the line. In the second row, since the predicted value is greater than the actual, the plot is above the line. Okay, so we can think about it that this is really relating to how the points are sort of appearing on the line. These values are really the vertical distances away from the actual linear model. Now, at the end of class, I asked you to take all the values in the residual column and add them together. If you did so correctly, you would get the value negative 0.6. And this is the answer to question 10. What is the sum of the residuals? Negative 0.6. But we really didn't get to talk about the second part of this question, which is why did we get a number close to 0? Does this mean that all of the residuals were close to 0? Well, actually, let's start with that third question first. If we look at the residuals, some of them are close to 0. For instance, this one here, 0.58. Here's another one that's fairly close to 0, negative 0.76. But others are not. I see a 2.51, negative 3.49. In fact, this is actually the worst prediction of all, because this is the residual that's furthest away from the line. So just because we got a sum that was close to 0, it does not mean that all the residuals were close to 0. Now, why did this happen? Well, we have to think about one of the main things we try and do when we fit a line is to create a line that has the same number of points above and below it. And by doing this, this means that we're going to get some over predictions and some other under predictions. And that will cause us to have both negative and positive residuals. Now, when you add together those negative and positive residuals, they're going to end up balancing each other out. And that's what happened in this case. All right, so since we had about an equal number of points above and below the line, the negative and positive residuals will balance out. And of course, as we saw, not all residuals are close to 0. The interesting thing to note about this is that we could have gotten a sum of the residuals to be close to 0 with the other line, the one we didn't choose. So I want to go back to the graphs from earlier. There they are. Now, if you look at the black line here, as the model you guys did not choose as the better one in class, if you look at the black model, the black line, there are 3 points below it, and there are 4 points above it. Now, if we calculated residuals here, we would find that even though these points are very far from that black line, they would actually balance each other out. And when we sum the residuals together, we're again going to get something close to zero. So that really doesn't help us determine whether A or B is better. I mean, visually we know which one's better, but mathematically we can't justify it by just adding the residuals. So we have to look at some other ways of using the residuals to justify the graph that we think is best. So you could turn the page. We're going to move on to exercise 11 through 13 now. So when we use a line to describe the relationship between the two variables, the best fit line is the one that makes the residuals as small as possible overall. So if the residuals tend to be small, what does this say about the fit of the line to the data? Well, naturally, if the residuals are small, then the points are close to the line. Okay? As we saw on those graphs, the blue line, the points were quite close. On the black line, the points were quite far. So the most common choice for the best fit line is the line that makes the sum of the squared residuals as small as possible. So we're going to add a column to the right of our table, and we're going to calculate the square of each residual and place it in that column. So we're going to go back to our previous page, make those data values reappear, and this column is going to be the residual. Let's make that a little more legible. This is going to be the residual squared. So we'd take 2.58, square it, round it to the nearest hundredth, like we've been doing. We'd get 6.66. Why don't you take a moment to pause the video and calculate the next few squared residuals. Okay. Did you get 12.18 for row 2? Did you get 1.10 for row 3? And did you get 0.58 for row 4? Hopefully you did. I'm going to give you the rest of these values to speed the process up a little bit more. So here are the rest of the values. 0.90, 0.96, 4.6, 0.90, 0.34, and 6.3. You can put them into your table. Again, you might want to pause the video as you do this. So we're back to exercise 12. So remember, we said the most common choice of the best fit line is the sum of the squared residuals. So if we go to that table, again, it looks like this, and we take the sum of these squared residuals, we find that it's somewhere in the area of 34.5. Okay, what we're looking to do is get this number as small as possible. Okay, and that's where the calculator comes into play. The calculator is going through a number of algorithms to make sure that the line that we are fitting is the line that takes the residuals, squares them, and then makes their sum the smallest. So why do we use the sum instead of just the sum of the residuals without squaring? Well, think about what I talked about earlier. That black line, this black line here, could actually have a sum of its residuals that is close to 0. It actually may even beat the other line. The reason is, as we take a look at these distances, look at these large residuals, right? But we have residuals on both sides. I have residuals above and below the line. These over here are going to get balanced out by these residuals over here. And we may get a sum that's close to 0. And it's a terrible fit for the data. So that's the reason that we would use the squared residuals and not just the sum of the residuals. Okay, so the sum of the residuals will always be close to 0. The squared residuals guarantees that we have positive values that still reflect how far the points are from the line. Okay, so once again, if we just use the sum of the residuals, we could have a very poor fitting line and find that it actually gives us a sum that's close to 0. And we might think it's useful, but it's really not. So the sum of the residuals in that exercise that we just did, again, was about 34.5, somewhere in that area. And we're going to continue on to the last page in this lesson. So the line that has the smaller sum of squared residuals for the data set more than any other line is called the least squares line. And this line is also called a best fit line or line of best fit. And this is what the calculator is finding. The calculator is finding you the least squares line when it does that operation, when you hit those buttons. For the shoe length and height data for a sample of 10 men, the line y equals 25.3 plus 3.66x is the least squares line. So basically it's telling us, hey, they've already done it. They've already done those computations, and they found that to be the least squares line. That means if we took the residuals off of this line, squared them, and got our sum, which was 34.5, we would never find another line that could get lower than 34.5. So therefore, that becomes our least squares line, which in turn becomes the best fitting line. So no other line would have a smaller sum of the squared residuals for this data set than this line. There are equations that have been used to calculate the value for the slope and the y-intercept of the least squares line, but these formulas require tedious calculations. That's what the calculator is helping us do. Fortunately, the graphing calculator can be used to find the equation of the least squares line. So right now, I want you to enter the shoe length and height data in your calculator and find the least squares line and see if, in fact, you get this equation. So you would go back to your original problem here. You would enter this data here in your list. I would pause the video at this point, enter these in, list 1, list 2, and do your linear regression, and verify that you're getting this equation here, which again is the least squares line. Okay, pause the video and do that. Okay, so assuming 10 men in the sample are representative of adult men in general, what height would you expect or predict for a man whose shoe length is 12.5? This you shouldn't need any help on. We know that the equations, that the reason we fit a linear model to this equation is so that we can predict. So we would take 12.5, substitute in for x, and the same thing with 11.9. So once you pause the video, go ahead and calculate the predicted height for 12.5 inch shoe length and 11.9. Okay, did you get 71.05 inches in height for a 12.5 inch shoe length and 68.86 inch height for 11.9 inch shoe length? Hopefully you did. So once you have the equation of the least squares line, the value in this of the slope and y-intercept often reveals something about the relationship that we're trying to model. The slope of the least square line is the change in the predicted value of the y variable associated with an increase of 1. Remember, it's a unit rate in the value of the x variable. So what's an interpretation for this equation for predicting height from shoe size? Write a response in the blank. Again, you could pause the video. So hopefully you realized that the slope of this was 3.66, and that would tell us that for every 1 inch of additional shoe size, we would expect the actual height to increase by 3.66 inches. Or you could say that in the reverse order. You could say we would expect an increase of 3.66 inches in height for each additional inch of shoe size. Well, the y-intercept of a line is the predicted value of y when x is 0, which we know. When using a line as a model for the relationship between two numerical variables, it does not make sense to interpret the y-intercept. Sometimes because an x value of 0 might not make any sense. So why does it not make any sense to interpret the y-intercept of 25.3 as the predicted height for an adult male whose shoe length is 0? Well, of course, we wouldn't have someone with a 0 shoe length and have them being 25.3 3 inches tall. It just wouldn't make any sense in reality. Okay, so to recap, let's go back to some previous pages. A residual is the difference between the actual and predicted values. One way to measure the appropriateness of the line is to sum all the residuals together. The flaw in that is that most lines, if they're balanced with points above and below, are going to get a sum of residuals close to 0. So we really can't tell if they're a good fit or not. To help us determine which line is better, we square the residuals, which we did in that by adding a column. Then we sum the squared residuals, and we're looking for the lowest possible number. The lowest possible number is something that the calculator finds for us, but now we understand at least what it is doing. Once the calculator has found that lowest possible sum of squared residuals, it calculates the slope and y-intercept for us. That's called the least squares regression line, or least squares line. That's the line that we want to fit to the data, and it's going to do the best job in predicting for data that's not in our particular original data set. We'll also need to be able to interpret the slope and y-intercept, which you guys have learned already. You should now be able to move on to your homework. And hopefully this was effective and helpful. If I left anything out or you're having some trouble, try and leave a comment here or send me an email and I'll get back to you. Thanks a lot, guys, and I'll see you in class.